So first of all, hello everyone, and hello to Crane, hello to Tomati, and hello to everyone else that is following. Hello also to um, all the groups on Facebook that are following me, or because I cannot tell from here how many there are, or how many followers actually I have. Um, or at least I do not know how. Let's put it this way. But yeah, hello to everyone. Hello to the group Phase 101. Hello, um, the group Retro Programmers Inside. Hello to the Amiga Malta Users Group and the Malta Vintage Group and Retro Academy. Fabrizio Radica. Uh, Hello, everyone. Sorry, I'm mentioning too many people. There are too many people that I need to say hello to um, before I start. And of course, a big thanks to Fabio Gucci, not Fabrizio, Fabio Gucci for his for letting me doing this stream. Um, Laurent, hello, hi. All those that are on Facebook, you're more than welcome to follow on Facebook, but please note when I send links or things like that, you will not be able to see them. Few things before I start. You should be able to see the message box where all the messages are happening. Um, you should be able to see both Facebook and Twitch. So can someone please confirm that you're seeing it and it's readable on the screen? Because that's what I do not know. If I have done it the right size, the box, because it's the first time I'm doing this. Message box not readable seems inverted. Ah, here it's not inverted. Okay, so this is this is always I cannot get it right. I'm going to remove it for now. So yeah, better like that then. So sorry, no messages. If it's not readable, then it's no use. Um, the stream title should be okay. Should say episode 3 for the English version. Okay, so let's continue where we left last time. So basically, where the last thing I said is that all the instructions, um, the 68,000 expects everything to be on an even address. Okay, um, as you'll get a guru meditation, our lovely guru meditation, and we will continue from there. Basically, so next thing that the book says or talks about um, is that, of course, memory can contain. Thank you, K1 K1200 RS21 for the follow. Yes, please. If you like what you see, please follow. Please follow me. Please follow us on Twitch. It's how to say. I do appreciate anyone that follows me, because that means that it's encouraging for me to see such followers, because I know that what I'm doing is helpful, because that's the aim after all this, to help others maybe follow my steps, and not necessarily this book, but can read other books and start doing 68,000 assembly. So yeah, remember that memory allocations are consecutive. Okay, so they start from 0. Let's say you start from 0 and then you continue till the end to the amount of memory that you have. And each memory location can contain either data or instructions. Okay, so an image is data, and instructions for the CPU is also using memory. So memory is shared between, or used, not shared, used between both things. One thing that you need to understand is that although we write the instructions like move.byte in the assembler as move.byte, okay, we are sorry, not we, the assembler will not store it in memory as move.byte, but it will store it as a value of 13F9. Okay, so the memory, I'm trying to mark it here on the screen. The memory um, is just numbers, and it just contains numbers, whether it's an image or whether it's an instruction. It's just we write it like that, so we write it in simple instructions, and the assembler converts it so that it's readable, because for us 13F9 doesn't mean a lot. Guys, give me a second. I forgot to check Facebook, that my stream on Facebook is okay. I checked Twitch, but I didn't check my stream is okay on Facebook. But yeah, it is. It is. Yeah, thanks, Laurent. I was referring to because I shared it on various groups. I was referring to my profile because that's the main one that it's reporting the correct thing. But thanks, Laurent. I hope I'm saying it, because I know it's French, but I cannot pronounce French. I'm sorry. So the instruction, okay, move 10,16, okay, it actually takes 10 bytes, okay, and the reason why it is so is because the move.b instruction is 13F9, okay, so we already know that move b is 13F9, but 10 is an address, okay, so because it's an address, it's 4 bytes, okay, and then 16 is also an address, it's another 4 bytes. So that is why it takes 10 bytes when you write move.b 10,16. So this might be a concept that you are not familiar with if you are used to 8-bit, because of course instructions do not take so much space in memory. Okay, but of course addresses are always 4 bytes in the 68,000. As I continued, the book continued to explain, even the no-op instruction, okay, which is for E71, takes 2 bytes, okay, so there's no instruction that takes 1 byte, okay, it's always 2 bytes. Now, what you need to understand is that the CPU has got let's say its own internal registers. We are used, for those that program the Commodore 64, we are used to, how to say, to have the accumulator X register and Y register, so only 3, and the rest is memory, and is just memory. But the 68,000 is more richer, okay, so it has 8 data registers and 8 address registers. In theory, it is 7 data registers, because A7 is the stack pointer, and it is not, you're not expected to use that, but it's also a register that you can use if you want to. So data registers we have from D0 to D7, and address registers we have from A0 to A7 also, and as I said, A7 is the stack pointer. internal registers, okay, and this is one of the advantages of the 68000 is that are a lot faster, okay. So we're using the internal registers is a lot faster than anything else, okay, than using memory or some type of addressing mode. So keep that in mind. You'll see lots of functions in 68000 that use the internal registers, and that is to keep speed basically, so they do not rely on memory or transfer between CPU and memory. Um, so that is why sometimes you need to understand what the address register, what the data registers, because normally they use the data registers um, for parameters, what they actually mean. Okay. Um, move.long d0 comma d2 is an instruction, is an internal instruction, is doing something internally in on the data register d0 and d2. So there is also other type of memory, which is the ROM memory, is where Kickstart is. Okay, you cannot write to ROM memory. Okay, so where the Kickstart is, somewhere in memory. I mean, the Amiga has got big range of memory. A big the address range is quite big, so they can afford to give 256K from the address range to or 512 for Kickstart. Okay, so the address, the only fixed address that has got a, let's say, a startup value and is always the same is address 4. Address 4 is a very important address in the Amiga. I'm not sure if it's in the 68000 per se. I mean, or 68000 like the Atari. I'm not sure if it's the same in the Atari's world. But for the Amiga, address 4 is from where everything starts. Is the first, when you switch on the computer, is the first memory location that is read, and it loads an address from there, and then it does a jump to that address, and from there it starts executing, which is an address to the Kickstart, I believe, and it starts executing. This address, okay, is irrelevant of which Kickstart you are using, okay. It can be different, it varies by Kickstart to Kickstart, I believe, but address 4, so the address that address 4 contains is different, but it always starts from address 4, and then it it goes according to what the Kickstart says. The programs that you use, okay, to load Workbench and uh, open Windows and all those things, they all use the Kickstart. The Kickstart has got libraries in it that are, let's say, the minimum libraries or part of the minimum libraries that the Amiga needs. Um, I do not want to go in detail. There are two types of libraries, those that are in the Kickstart, okay, and those that are on the disk, okay. In today's world, it's on the hard disk because nobody uses the floppy anymore, but in the old days, it was on the floppy. And the Amiga, if doesn't find the library in Kickstart, it goes and tries to read it from the libs directory of your floppy drive. And then if it doesn't find it there, then it tells you this library is missing. So that's roughly how it works when it's looking for libraries. Sorry, when I'm pausing, I'm just making sure that I didn't skip anything. The author continues saying that if you are like if you want to run games or demos, um, and you just use as copy, sorry, if you are writing demos, okay, or games, um, you are, or something like Xcopy, okay, you are actually bypassing the OS, okay, so that's why they do not have the intuition way. Um, Normally demos do not run from Workbench, but they have their own loader actually most of the time, so they don't even use what the Kickstart provides, um, because demo coders want to optimize as much as they can. Um, that is why um, they do it. They do so. Games do the same thing, unless they run from Workbench. Um, those that do not boot on an OS, so which is many of them, okay. Normally they are not using Kickstart at all, or if they use it minimal temporary and then they shut it down. In theory, okay, what we are going to do here with this book, and this is just theory, so don't go and do it, please. If you remove the Kickstart ROM from your Amiga, you should still be able to execute your code because it doesn't need Kickstart. But that's theory, okay? In practice, it's a bit different because if you remove the Kickstart ROM, it needs to boot from somewhere. It needs to know from where to boot. So actually, it's not exactly right saying that. The book says that, and I um, tend. I don't want to say I agree with it, but also disagree with it. It needs to boot somehow. So yeah. Hi, Chicolop TSA. Hope you're well, and thanks for joining. Um, you can probably say better than me, Chicolop, what about demos that they use their own loader, and basically they do not use Kickstart at all. I mean, Fabio here is referring to that fact, and actually you do not need Kickstart because of this. But as I said, don't try to remove your Kickstart. Yes, exactly. Boot block and self-track. So yeah, it's their own track loader basically. So they just use the boot block. It boots from the boot block, and that is it. Because floppies on the Amiga has got a boot block, and that is what makes them boot. It reads that, and it starts booting. Um, I'm not sure I skipped one here, I think. So when you're using programs that do not use the OS, like Workbench, it is very evident there is no multitasking. I mean, to use when you're talking to the hardware directly, there is no OS, so there is no multitasking. It's the OS that provides you with multitasking. It becomes, let's say, I don't want to compare it, but it becomes like the Commodore 64, that it is just, the Commodore 64 is not multitasking. It's just you have access to the hardware directly and nothing else. So that was what was added by when we say the Amiga is multitasking, is because the OS is multitasking. Okay, so the hardware has the right hardware to make it multitasking, but you need to program that hardware to make it multitasking, of course. So in short, the ROM or Kickstart is a set of routines that enable to talk to the hardware and make life easier. Okay, so that's what it is. Demo coders don't really use them. It's hard work not using the. You have what? 128? Well, yeah. Um, so it's really hard work when you're programming the hardware directly. Okay, so it's not like when you have the OS. There are many routines that can help you with that. Yes, you need chiprem. I explained chiprem in the last episode, so I'm not going to explain chiprem again um, um, in terms of where we are. But yeah, I already explained what chiprem is, so um, just not to confuse or repeat, because I really would like to finish this and start number two, uh, where we are. So, okay. So we will be coding things without using the ROMs. Okay, we will do everything using the custom chips and talk to the hardware directly. The custom chips, many of you already know this, are Paula, which is good, which is for music. Agnes is for blitter and copper. Denise is for screen and colors. And then there is CIA and B, which is I don't know exactly how they are divided, but I know that they have control like floppy and all that stuff. What you mean? You have revision 6.0 and you have no chips? Not sure what you mean, but I'm talking about Amiga standard, and for sure you have some type of chips to make a real Amiga boot. Once you know all the 68K instructions, okay, you can create large programs, but the 68K instructions on their own do not produce anything, okay? You need to use the hardware registers. Yes, you have Picasso, but you still need Kickstart. Um, to boot. Picasso has got its own RAM, so if you're referring to that about chipmem, but that's a different story. And to be honest, no games, no demos use that, as far as I know. It's only for the OS to make things nice. You need to switch to the old famous, let's put it there, custom chips to use the games. So anything that we do will not use something like Picasso. We need to program the hardware registers to get sound and vision or GFX. Use the blitter to draw lines and copy things around. Most demos that use the blitter to draw things and the CPU to do calculations. So basically what we are saying here is it's like having two processors in a way, okay? The CPU is doing its calculations, but the blitter is doing its own calculations or movements. It's just move blocks of memory, okay? And through that, it's achieving you achieve the graphics that the Amiga can provide. So it's like having two processors in one computer. That's why it's called coprocessor, because actually it's there to help. It's helping the CPU and it's running alongside the CPU. To display anything on the screen, you need the copper. Okay, so with the copper, you can program the screen, change colors, etc. So DFF 180 is color 0, DFF 182 is color 1, etc. etc. Um, there are registers that you write to and there are registers that you read from. Okay, so not all registers, not all custom registers are read and write. Actually, they are either read or write. And some, they have a bit that you change, you flick, and it becomes read or write. Cyclop can say more about this. He knows them by heart, I believe, more than me for sure. um, DFF006 is the raster line. You read where the raster line is. It's a read-only register, not like the previous two that I mentioned, the FF180, where you write to. Okay, so you're putting a color register, a color into the register, while the FF006 you read from it. Okay, you read where the raster line is, and this can a raster line is updates the screen either 50 or 60 times per second, whether you're PAL or NTSC. Okay, if you're PAL, it's 50 times per second. So registers can be either read or write. In registers that start with BFE, okay, we know we're controlling other things like, as I said, the floppy drives, and programming, I don't know, the ports or the joysticks and things like that, or the mouse. So BFE001, you can control the left mouse button. This actually is how our first program, what our first program will use, okay? Our first simple program that I will demonstrate in a minute, given that we arrived to the last page. So how to use ASIN1 and ASIN Pro? So this, I need to show you, I need to exit from here. So when you enter, I know I did explain this, but because the book is referring to it, I'm going to explain it again. When you enter into ASIN Pro, you select where your sources will be. Okay, so you can either put them in chip mem if that's the only thing that you have. You'll get only that type of mem. If you have an Amiga 500 with 512K, then your only option is chip mem. If you have an Amiga expanded to 1 MB, then you get fast mem or public mem. You select public mem. Public mem gives you the option of either putting it in RAM, which is fast, or in chip mem. The assembler decides. Normally it goes for fast mem. Okay, and absolute is something that when you want to program at a specific address, which normally is not used. Okay. Let's continue where we were. Yes, there's actually, let's move it out of the way so that I can follow it better and show you on the screen. So if you use the V command, okay, it gives you where are you, in which directory you are, and so I'm in the directory ASIN and where I am as a starting point. And if you use, I need to get my other notes. If you do equals, okay, just equals, it tells you where your workspace is for your source, where in memory your source is, okay, which workspace you're using basically. So as you I don't know if you noticed, but this is the amount of memory that I reserve for my sources. So that's what I have basically. Oh, it continues. So there is, I have to take it out again and continue to read. So if you load, let's load a source. tutorials, RamJam, sorgenti. So this is our first source, and if I go to comma, where is the window? I need to be in the editor window. So you can see that in this window we load it. It's F1, but we can load others and we can switch between the other sources. So if I go to F2, if I press F2, okay, I have nothing there, but I can load another source here. Let's load um, lesson 2. Okay, so this is the first source between lesson 1 and lesson 2, and then you can see you can switch between one and the other one. Okay, so that's how you switch. You have from function 1, F1 to F10 to switch between them. I'm not going to show the text because I think this part is just the assembler. So I need to read while I show you on the screen. Yeah, going through the source, okay, it is, you can move the cursors, okay, up and down or left and right. But then if you press shift and the arrow up, you go up one page or down one page, okay? So that's another useful thing to know, okay? I'm not seeing the messages right now, so if you're writing something, I do apologize. I cannot see the messages while I have the other because the other my text is covering. If I do A is assemble, and if I do J is execute, okay, which I do not wish to execute it right now. I want to leave it for when we arrive there. As I said, labels always start at the beginning of a source, at the beginning of the line, like wait here is the first character. I will come to the messages later when I put the text back, but right now I cannot have both of them at the same time. um, use letters and numbers for labels. Okay, I think this is common sense. I do not need to be repeating that. Let me do something. Maybe I will be able to see the messages too. Hi, Lorenzo. Hi. Thanks for joining. Um, so, sorry, I'm just making sure that I am not. I know I need to read sometimes to make sure that I'm not skipping anything from the book, because as it's not fair also, I promise to go through the whole book. So that's why. So this I already explained, but the book refers to it again. Equal R is the registers, okay? So you can see the registers. And J, I also explained that basically he's preparing us to execute the code. That's why he's doing all this. And J is to execute the code. Escape is exiting the exiting the from, if you do registers like I was here and seeing the registers. Escape is stopping from seeing that. I have a note. Okay, so the book guarantees that this works with Kickstart 3.1, of course, because when it was written, I think it was written with till Kickstart 3.1. But you know that there is Kickstart 3.14. So although actually I'm not running Kickstart on, I'm not running on Kickstart 3.14, but I assume that there shouldn't be any issues. To be honest, we're just going through the hardware directly, and I don't think there are issues. Um, Cyclop, do you know if there are any issues using the hardware? Because when we're using the hardware, if we are um, let's say accessing the hardware directly on a Kickstart 3.14, I don't think there is, but I do not know. I haven't tested it on 3.14. Um, Guys, I do apologize for sometimes my bot is displaying messages too frequently, and I think that is because I programmed it wrongly. So I need to check this. I mean, there's so many things that I need to do with Twitch offline, and when nobody can see what I'm doing actually, and it is annoying. um, The sources are also compatible with A1000 and A4000. So we should not have any issues in relation to that. Okay, so yeah, I think we have finished, and I hope I'm right. We have finished. Yes, we have finished chapter 1. Hurrah! Yes, I need to say that. Um, so yeah, so now we are in aligned with the Italian version because the Italian version finished. I finished it in this at this point, but eventually I want to align them back. So today we're going to be ahead of the Italian version, but I will make the Italian version longer next time so that they are aligned. So it's time that we execute our first program, and then I will explain it, what he has done. Okay, so assemble NJ. I mean, nothing spectacular. Okay, it's just the colors of the Amiga just being poked. It's like poking the Commodore 64 with all the colors and an infinite loop. That's what he's doing here. It's the same thing, but he's doing it very wisely. So I already covered that register DFF006, okay, has got the current raster register, okay, and instead of we are just reading that, it's just a value, we just need the value, and we are putting that value in DFF180, which is the colored 0 register, which is always the background color register for the Amiga. So basically we're copying what DFF006 has into DFF180, and like that we then I'm going to skip this line. We then have a loop, continuous loop, branch or not equal. So we're doing some test, and we're jumping back to wait mouse, where wait mouse is just a label which represents the memory location where move.w is, okay, to start executing. So basically it's a loop constantly filling up, changing the value in DFF180, um, so that um, we see that effect on the screen. Now, line 7, it's bit test. So we are testing for 1 bit, okay? And we're testing that this bit is 0. So basically, when the mouse is not pressed, the bit 6 in BFE001, okay, it's another hardware register, okay? But it's not where the graphics or sound is, but it is where the CIA registers are. Okay. Um, this bit 6, we're checking that it is not 0. So when we press the mouse button and we press the left mouse button, okay, so this is testing for the left mouse button, okay, sinistro means left, okay, we are checking for that, and if it's pressed, we just basically exit the loop. So then it branch or not equal becomes not valid anymore, and we return back to the OS, or in our case, because we are running it in the assembler, we return back to as in Pro. So now the book, I just want to show you what I need to explain, because the book really goes in detail here. This is like another Bible, okay, that one needs to read after his text, after the source, okay. So he explains what happens above, but goes into a lot more detail, which I'm going to go in a minute. So I just explained it, but that is my version of explaining it. Now he goes in and explain. Just for the sake of this course, I suggest to all of you that are interested in following this, um, that you download the sources. I send the links several times for this book, and actually maybe I should send them again, and download the sources so that you can try them out yourself. I mean, of course, you will not understand the Italian, but that has nothing to stop you from executing the sources and modifying the sources. The sources you should still understand. Um, Let me find the page again. So I'm just going to type it in the. So that's the link for the course, for the PDF, which and the sources. However, I also suggest that you download the sources from Aminet, because I think they are more updated than the ones that you find here. Um, it's up to you. Um, I'm using the ones from Aminet, but I do have also these, and sometimes I do compare them. So that's the reason why I'm mentioning this. Um, Now I'm going to jump to the second book. Okay, the second book is the big book. So notice I have two books open. One is the 404 that has got 404 pages, and one that has got the 187 pages. All the examples are in the big book in the 1872 pages. Okay, so I'm just going to, I mean, some of these things might be the same like what I already explained, but I need to go through to what it says. The first thing before I start, actually, it talks about the license and what type of license. So that's somewhere here. Yeah, it's just to make you aware. You can distribute it. You can do what you want as long as you don't change his name, basically. Um, and as far as I know, I don't think you are allowed to modify it neither. But anyway, so the first line, as I said, is copying from the raster line to DFF 108. Then, and it's a move word. Yeah, that's something that I missed. I should have said we are moving a word. We're copying the contents of DFF006, which are word contents, and we're copying them into register DFF180, which is also a word content. Okay, so you can actually copy bytes. Okay, so I'm not saying you cannot, but the hardware registers are word aligned and they are word um, registers. Then we test for the left mouse button that it was pressed. So that is something that I already explained. Now he explains that the next line was branch on not equal or branch on equal. Okay, he had branch on not equal, but he makes us aware that there is also branch on equal. In our case, we did not need, I mean, branch on equal did not make sense to put branch on equal there, but we needed to loop, we needed branch on not equal. Okay, so just know that like there is branch on not equal, there is branch on equal. And remember that branch on equal works on the 0 flag. Um, we are reading the value in the DFF006, which is the current line, and storing it in the FF108, which is the color register. So I'm quoting this because this is happening very fast. Okay, as I explained, you see all those colors on the screen. I just read exactly what he said there, just to make sure I'm not skipping anything. Remember the values. Okay, so the values in the color register, which is DFF180, okay, takes the format of red, green, blue. Okay, so there is one nibble for. Remember, one nibble is 4 bits. One nibble for the red, one nibble for the green, one nibble for the blue. Okay, so and the first one, so if we take a color, okay, let's say we are doing OFOO, the first zero, the first nibble is not is ignored, okay, at least on ECS and OCS chipset, okay. And then we have a nibble can have a number between 0 and F in hex, okay, between 0 and 15. So we have the red, which is the maximum red color, so we put F there, and then we have 0 and 0. So this is, we are putting a red color in the background register. Why we have 4096 colors? Why the Amiga has 4096 colors? If you notice, we have as I was saying, we have from 0 to 15 for the red. So same for green, same for blue. So if you do 16 times 16 times 16, that means that we have 4096 colors to choose from. Okay. Bit test. Test for a bit position if that bit is 0 or 1. You already know this. In this case, we are testing for bit 6, and if this is 0, we know that the left mouse button is pressed, as if it is a 1, we know that it is not pressed. You can substitute bit test with bit test #2, but notice we have a 2 and we have a DFF016. So instead of testing for the left mouse button, we're testing for the right mouse button. Okay. So this is another way we could have tested another way of, instead of waiting for the left mouse button to be pressed, we could have tested for the right mouse button to be pressed. And if you want, you can go and change this in your source and execute it and see if you have the same result, basically. If you assemble an executable, you can write the exe of the file by doing WO, okay? And then it tells you where you want to store the file, and you give a file name, okay? By the way, all the commands that I type are shown in the menu depending in which mode, and it tells you what are the commands. Okay, so you can see RW, okay, WO, sorry, um, is write object. Okay, so we are in the right menu and we are writing an object, so it's our exe. Okay, so same for read. I'm have the habit of typing R, but you can come to the menu and select read source and it will read. I mean, it has more commands than actually there are in the menu, I believe, but um, most of them are there, just to make you aware. Um, an interesting fact. So I covered that there is .b, .b, .w, and .l, but there is also .s, which is also the same like .b. We use .s because it makes more sense than using .b. It means a short branch instead of a longer one. Okay, so that's why we use a .s, and it's like putting a .b, but we use a .s. It's just notation. That's what it is, and nothing else. Um, Crane, I just saw. Ah, okay. I understood what you mean now. Okay. Sorry, I thought there was an issue. Um, yeah. So far so good from what I can tell. Oh, ciao Fabrizio. Grazie per essere qua. You're trying to learn English, I assume. uh, okay, so um, I didn't see your message, Fabrizio. I'm seeing it now, but yeah, thanks for joining. Um, I know you struggle to uh, say things in English, but I hope you're understanding me. Speaking English, let's put it this way, with my funny accent, English accent also. Uh, so the .s, it means that we can go, we can branch -1 to 8 and +1 to 8, 1 to 7. Okay, so the branch is not that you can jump wherever you want. You are limited. That's why it's called short. How long, how backwards, and how much forwards you can go to. Okay, um, that's one of the things to keep in mind. Same if you have, instead of .s, you have .w, you have -32768 and +32767. Okay, um, so yeah, it's a relative branch from where you are, how far you can go, what is the distance that you can go. In fact, the book mentions, I'm just going to bring the book back. In fact, the book just mentions that it is here that, uh, where did it go? Oh, I clicked in the wrong book. Okay, so it mentions it that there is branch, my God, there is branch, so BTW means by the way, not branch, okay? .s or .w, okay? If you use .l instead of .w, okay, the assembler normally will change it to .w. You cannot you do .l as a branch, okay? Um, so the assembler is intelligent enough to change that. So it's doing some work for you if you make such typos. Hello, Antonio Delia. This is Antonio, questo è per in inglese, la versione in inglese, non la versione italiano. La versione italiana sarà la prossima settimana. Allora, so, my God, I was going to continue speaking in Italian now. Try to be as accurate as possible. I mean, although the assembler will fix these typos, but not all assemblers do. Depends which assembler you use. I mean, I know that Dev Backend, as in Pro, fix this, but I do not know if like something like the basic one, the A68K, will actually fix such a thing. So yeah. Okay, so I think I finished explaining. Ciao Lorenzo, then thank you for the follow. I'm pretty sure you're joining for the Italian version. Okay, so sorry guys, I just received a message that I need to look at because I always need to check if there's something wrong with the with Twitch or Facebook, but no. So we can continue. Okay, so today, okay, so we've done 1 hour, so it's the right time for me to take a break. Also, since I do need to take a break, uh, I will be back in 5 minutes. In the meantime, I am not. I'm going to try an experiment today. I'm going to do the thanks in the middle of the of the um, of the stream, so that at the end I would like to try to raid a channel, a Twitch channel, given that I managed to figure it out. So yeah, so the thanks is going to come before the normally I have the be right back, but today I'm going to do that. So don't think it's finished, okay? Hello again. Can you hear me? Can you please let me know that's all okay? Okay, thanks for letting me know. Okay, so I hope you all had a break like I had. I mean, the break is not just for me, but it's for everyone, to be honest, because I can understand that watching somebody, we all have our needs in a way. Okay, so we finished chapter 1, okay, and it was a lot of talk, okay. Chapter 2 is also a lot of talk, but with a difference. And the reason why I'm saying that is because now it starts talking about the processor, about the 68,000 itself and its instructions. And in chapter 2, we are going to cover addressing modes, okay? There is one addressing mode that he doesn't cover, and he does it intentionally, which I will explain. But he covers them all. His examples are brilliant, seriously brilliant, for beginners, so that they can understand. Um, what I want to say is that it also contains lots of work, lots of text, but it also have lots of examples. Okay, so we'll be switching between the assembler and the book quite often. And trust me, now if you don't have the sources in front of you, and try or the Amiga in front of you and trying. Hi Amok. Oh, thanks for joining, Amok. Um, yeah, sure. Okay, no problem. Thanks for joining anyway. The little that you can. I mean, of course, you can catch it up later. By the way, you just remind me of something. Uh, the videos of these will be available on YouTube eventually. Right now, I'm organizing how I'm going to do this, and I've done some editing of them, and I'm not quite happy yet with the result. So that's why they are not there, but they will be there. So whether it's in English or Italian, you'll get them. You'll get them on YouTube. Um, yeah. So for all those that, because I know that Twitch keeps them only for 2 weeks, I think, and then Twitch deletes them. On Facebook, they are there. They remain there. You just need to find them. Um, so yes. However, on Facebook, it's not the same like watching them on YouTube. So I do suggest that you also subscribe to our YouTube channel, so that you can follow. If you miss one, you can follow. Um, so that you can follow the whole um, series of the book. Um, Also, just right now, I am just considering how to do this. Okay, so we as Phase 101, okay, we were a group. We are not were, we are still are a group, but we used to be a demo group, okay, which I have to say I'm not to that level at all, to where I was. Neither me nor Crane are to the same level that we were um, 30 years ago. However, we don't have all the sources that of our demos, and we don't even have the images or music for our demos that we did. However, on Demozo and some other websites like Burnett, I mean, I do not know how to say them properly. There are our demos there, and because we have some sources, okay, and not necessarily sources of those demos, but sources that might have led to those demos, okay, or intros. I am thinking of organizing, of doing another series besides this one, of coding, um, of going through our sources, trying to understand what the heck we made, what we did 30 years ago, and from them, I hope that anyone else can learn. Um, so yeah, it's a walkthrough, um, going back in time for myself, um, like anything else when it comes to the Amiga for me. So I'm thinking of having this series, of dissecting our own demos, of what we did 30 years ago. Um, I have to say, I will not show the scroll text or some of the comments because 30 years ago we were not kids, so we did right things. And I don't want to say Crane wrote things, but I want to say Prince wrote things that if you had to read them in the source, it shows how much careless and how much we didn't care about what we were doing or what we were saying. When you are 18, you really don't care. Um, you just don't think twice to offend somebody, whether it's with a demo or in a text or in a source. So yeah. Um, it's the dark side of Phase 101, let's put it this way. Uh, but we didn't really crack games. We were more interested into doing demos. We did crack some at the beginning when we started, but there was no copyright law. in Malta at that time. But then we saw that we are not really interested. We were more interested in demos, and yeah, we started doing that. But today, if you tell me to do a demo, I don't even know from where to start. Even though I understand some stuff related to the Amiga, uh, no, I cannot. And I hope going through this book with you guys, actually, this book will let you learn to do certain things in relation to demos, but it's it's one of those things that you need to practice and do and try things um, than anything else. Um, okay, so let's go back to chapter 2. So as you see, I'm still in book number 2, the big one, but I need to jump to the next one and see chapter 2. See this number 2. Okay, so he says something funny here. I didn't put it in my comments here, but he says really something funny. If you uh, seen example 1 and it is too much for you, then this is not for you, he says. So it's funny that he says this, but yeah. Uh, so I hope you understand lesson 1. It's really basic. I hope you understand the source. That's what I mean by understanding lesson 1. And I hope that you understand where this is going to take you. Okay, it's not an easy path, but it should um, let you into writing code for the Amiga. So he says that we start by learning the 68,000 now, of course. And what he means by that is actually covering the addressing mode. He's not going to cover the instructions. The instructions, although he will use instructions, of course, and he will explain them while he's using them, but he's not going to go through one instruction by instruction and explaining it. It doesn't make sense. That needs another book by itself. There are so many books on 68,000. So um, I do encourage you to look up the instructions of the 68,000 if you do not know. And I have even shared a book with you guys, which is this one. Okay, that talks about this. It's only the 68,000 instruction set. And what we are going to cover today is this. This is the addressing modes of the 68,000. Okay, he will not cover this mode, this addressing mode. He will not cover it, um, but it's not a big thing. You don't need to. Um, you don't need to worry about it. But all the instructions are in this book. Okay, one thing I need to follow to say, there are different ways of writing certain instructions. For example, d bracket an can be written, or d bracket an comma x I, whatever that is the index register, is written. You can put both of them in a bracket basically, and same for the other one. Okay, um, I will come back to it, but it doesn't matter. The assemblers understand both ways. It's just the new notation they call it for the 68,000. Okay, so let's continue. Okay, so this chapter, the listing in chapter 1 shows that the CPU by itself doesn't do much except organizing things and moving data in memory. As you saw, to put colors on the screen and check the mouse, etc., that was not the CPU. The CPU was executing instructions, but it was using the hardware registers to do that, okay, to put colors, etc. It needs the Amiga custom chips to actually do something interesting. It moves / manipulates data in memory, where hardware registers are to be able to do some kind of GFX. So basically, it moves data between hardware registers and then they do something. Learn to address range, okay, to address addresses basically. When you see the FF, okay, or BFE, you know you are um, you know you are um, you talking to the custom chips, okay. So always keep that in mind when you see DFF or BFE, sorry, and then of course XXX can be any number. We are talking about the custom registers. You just modify, update these, and things will happen on the screen or on something, okay. Basically you are just programming the hardware registers using the CPU. Um, it's repetitive, this sentence. To do a game or demo, you need to know the hardware registers, what they do, and you will use these quite a lot. It's a repetition of what he said before. So you need to know the hardware registers like the 68,000 instruction set. Yes, this is quite true. You cannot just know the 68,000 and think you're going to do something on the Amiga. You need to also know the hardware registers of the Amiga. The Amiga is not like these board computers, you know, where you learn the CPU. Okay, you are actually learning the CPU plus its custom chips. Okay, as stated, no libraries from the from the Kickstart ROMs will be used. However, there are exceptions, but these will be minimal. Okay, example of this is alloc mem. We will need to allocate memory to um, do this, basically. Uh, Please note, when we are working using Workbench, you are using the multitasking, this I said, while when we are doing using the hardware, there's no multitasking. And also because there's no OS, you get the guru very easily if you make a mistake. Okay, so you need to fall in love with guru meditation because you'll see it quite a bit when doing assembly. Uh, okay, so here I'm just going to share this link again. I shared it last week, but I'm going to share it again. Uh, it's info about the 68,000. There is no really good web page on the 68,000. It's a shame, not like what there is on the Commodore 64 for the 6502. Sorry, but yeah, nobody has ever done something like that. Maybe it's a hint for somebody out there listening to me that we should have a page related to 68,000. Somebody that someone can search for and do things in it. Uh, okay, so what we are going to learn here is number one, the 68,000 addressing modes, and two, the CPU operates on memory and that each memory location can contain a byte. Okay, this is something that we know. And then he will cover again. He repeats it quite often. This one, as you saw in the, he will go again through hex and binary. I will not go through that. I mean, if you really want to learn hex and binary, if you haven't done that, uh, then maybe this is not for you. As the book says, you need to know hex and you need to know how binary works. But here I made a note. Hex numbers use the numbers from 0 to 9, A to F. Okay, so we have base 16, so it's from 0 to 15. And the symbol for hex is dollar. Okay, binary use zeros and one. A byte, so it's a repetition. I'm just going to read what he wrote down there in the page. So here, Okay, binary uses 0 or 1. A byte is 8 bits of either 0 and 1. Enable is 4 bits of either 0 and 1. As the symbol for binary is percentage. Okay, the assembler, I covered this also. You can type question mark and then the number, and it will convert it into hex. Okay, hex numbers are used a lot since it is easier um, to talk to the machine basically, and makes more sense to the machine. Of course, in reality, everything's done on a computer is in binary. Everything is stored in binary, in the end on a computer, even though we uh, have hex. But that is reality. Okay, he's going to use the instruction clear, so CLR, to give the first few examples. Okay, so what does clear do? Clear clears um, the memory address that we are pointing to. So in here, he's clearing address 40,000, sorry. It's a byte, so we are only clearing 1 byte. But if this was a W or an L, we will be clearing either 2 bytes or 4 bytes. Okay, and I'm going to share another file that I shared in the previous um, thing, in the previous session, for you to um, for you to let's say, to help you out. As I said, if you're on Facebook, you will not see these links. You need to be on Twitch to get the links. Okay, so this one, okay, this type of addressing mode, and that is absolute. Okay, that is absolute addressing. So basically, what absolute means is that we are doing something on a memory location which is fixed. I just want to, because the book, that's one thing that is very different from Italian to English. The book doesn't use the exact words that we might be used to in English. Okay, so I'm just making sure that when I say the addressing mode, it is the right one, the right name. So I should had opened the book before I started and I forgot. So um, just give me a moment so that, but to be honest, we have them also in that book. So yeah, actually we have them here, so I can refer to them here. So when we have a memory, see, absolute addressing. So clear dot w or dot l or dot byte is absolute addressing. Okay, I'm noticing that dot byte is not there actually in this book, but yeah, you can have dot w or dot l. The I will come later to when we are doing AN, because AM means address register. Yeah. So I think he's going to modify. Actually, this is what he's going to do. He's going to modify a bit the initial code that we did. Okay. So instead of using an address like 40,000, we can use a label. So first of all, we could have put a label instead of 40,000, okay? And I know why he's doing this, because some people get confused on this. Um, he goes to explain how to modify the program in chapter 1 to use this method of absolute addressing. So in here, okay, in this example, okay, we have line 2 is the same like in the original example that we had in chapter 1. This line for testing the mouse is the same, okay, and the infinite loop till we press the mouse is the same, but instead of between the branch or not equal and the RTS, we have a clear, okay? So we do not before we had an RTS, so he inserted the a clear, and what he's doing is he's clearing, and as you see, he's using a byte, a label here. So he's clearing this address, okay? He's clearing this address, okay? So we had in it 30, okay? But actually, when we clear it, it will contain 0. And I think he also explains. Um, so also this can be, remember, it could be a byte, a word, and a long word. So it depends what we have. So he is explaining what I just explained here, that you can use a label instead of an address. Okay, so wherever that is, he's using a label, and that is absolute addressing. Okay, um, so we can, okay, do this in our code. I'm not sure if it's part of example 1. So let's go on to the assembler now. So I will be switching quite a bit between the assembler and the document now. And unfortunately, the screen is not big enough to have them both, and also the Amiga. So yeah, uh, we did load it. Okay, so the actual example is more complex. So let's go to example 1 and let's add, okay, what he says. So clear.byte, and we call it data 1, and we put data 1 define constant byte, and we put 30 in it. So we can do one thing now. If we assemble it, oh, oh, typo. Okay, so we assembled it. So now if we do D and wait mouse, okay, we haven't run it yet, okay? So we have our program, okay? And you can see that move W is taking what I discussed earlier, the 10 bytes from memory. Actually, it's taking, is it taking more? 1, 2, 3, 4, 5, 6, no. No. And you can see 33FE, F9 is the instruction. Then the address register, okay, so DFF006, you can see it here, and then the other address register, okay, 00DFF180. So we had DFF180, so which is our, because the zeros at the front, we don't write them normally, so just to, but the assembler, when it assembles it, it needs to write them, no? So clear byte is clearing the memory 40217A4. So 40217A4, it is this byte, and you can see that we have 30 in it. Of course, the assembler does not know that this is data. Okay, so he tries to continue to assemble instructions. Okay, and show us it, but actually that is our data is. Okay, and it's after our RTS. You cannot put the data and then the RTS. Okay, so just to be clear. So now if we execute it, okay, and exit, we should be able to see the, wait, mouse. We should be able to see that the memory location was cleared, as you can see. So we are clearing byte, remember it's a byte, at this address, and this address, the content that was 30 now has got at 0. Okay, so I think this explains it quite clearly what we have done. Okay. So hello Philip, thanks for joining. Uh, Thanks for joining in on Facebook. He introduces something else in this code. Okay, he introduces the concept of the assembler directive define constant, and define constant can take either, it's a directive of the assembler, okay, can take either a byte, either a word, or a long word. Okay, in this case we are defining a byte. Okay, you can type lots of things, so you can have text, and text you write it in like this. So as define constant byte, the text, in my case I wrote greets phase 101, and then a text is always terminated with a 0, a null. Okay, so you need to put a 0, and it's very easy to forget putting that 0. Okay, so just to make you aware, and this is where many times you'll see a guru because you forgot to do a 0, so that you align so also the text. Normally also between this one, something like this, and another one which is not covered yet in the book, but I can show you by, just to be sure, okay, that we are correct and we have the right alignment. Okay, because with data you do so hello Michael, thanks for joining. um, you do even, so that the address is aligned properly, so you're always on an even address. Okay, if you had text and you put the comma 0, you don't know how long the text is. It could have been 16, the text, and then when you put the null, because it needs a null, then it becomes 17. So then even will correct that by inserting another byte to make it at an even address. So yeah. I need to figure a way of switching between the Amiga and the textbook much more quicker. It's annoying, I have to say. In fact, I mentioned it in my text that there is a directive. Even he didn't mention it, but I did mention it just in case. Okay. He shows that the directive, the define constant, can take byte, word, and long word. What I just said, basically. Okay, so he's going to talk about strings, what I also just showed. So strings end up with a 0. So you need to make sure that after it, you are on an even address. So, okay. Ciao, Emanuele. Thanks for following. Um, I was saying uh, the instructions, okay, can also be written. There are an instruction, if you go into if you had to read a book specific to the 68,000, you will find. I'm just going to switch like this. I think is the best way. You will find that you can write an instruction, okay, just like this. So move.l. Sometimes you do move.a. You see the move.a.l or move quick dot moved quick. It's always .l, I think. These letters, okay, most of the time you don't need, except for quick, I think, you don't need to specify them. The assembler is intelligent enough to know which mode you need, which move you need. So move.long and having the 0, comma the 1, okay, and move 80, comma the 0 as an instruction is different. Okay, so the number for the move, not so it's different. So to distinguish, because we're using an address register here, so it becomes move A, but you don't really need to do that. It's the assembler will know, but sometimes you will see it either when you do a disassembly of something, or somebody wants to be um, precise. However, move quick is something that sometimes the assembler converts. You have an option to tick and to convert certain instructions into move quick. However, I am the type of person that I prefer specifying it and showing it uh, that it's a move quick instruction, because there's a huge difference in speed if you use a move quick instruction to the other ones. I mean, move quick is a lot shorter. So that's why um, it is um, it is important, especially if you're aiming for speed. So let's see if the book comes back the way I did it now. Okay, I think this method is better. Yes, here I am showing. You will see that move A and move, they have a different number in memory. Yeah. Okay, so just to read my note, add quick. So I put move, but you can have add quick, and it's a byte. So um, normally, actually, I put move quick.l. That cannot be. It has to be byte, and the reason being is that quick is only works only on a byte, only on a certain range. Let's put it this way. I think you can have at quick from 1 to 8, I believe. But for detail, specific detail of this, you need to read the 68,000 manual. Okay, so this is something that the book doesn't cover, and you will learn these along the way. So expect me to make some mistakes when it comes to the instructions, because there are so many, and although there is one move instruction, in reality there is not one move, but there is a lot of moves that are different, and each one of them has got a number, how it is stored in memory. Okay, so let's hope I will manage to do at least the first lesson. We have arrived to example 2, the first one, to A, okay, and we're saying to go for it basically. So same thing. Now this one I do not want to save, so it's going to ask me that I'm going to lose everything. Yes, continue, and we arrived at 2A. Okay, so he's taking the same how to say approach of the first one, but let's say he enhanced it. Okay, so what he's doing, okay, so are we pressing the right mouse button? Okay, if we are, we if we are, we go to here, Ajunji. If we are not, we test for the left mouse button. Okay, and if we are, we go back. Okay, we go to the top. What if we are not, if we are, we exit basically. Okay, so we are testing for bit 2 of DFF016. Now I need the book to remember what DFF016 is. Actually, it's the mouse. No, I just said it, but still I need the book to read the comments, my own comments. So I'm trying to find out where the first example is. Okay, so this is what the program does, and I'm reading what he says. It waits for you to press either the right or left mouse button. Each time you press the right mouse button, a counter is incremented. Okay, if you press the left mouse button, you exit the program. So basically, when we press the right mouse button and we jump into here, what are we doing? We are storing, we are adding actually. First of all, we are storing what there is in contatore, okay? What there is in contatore to DFF180. But we also adding, and look, it's at q.byte, okay? So it's a quick one. We are adding one to counter, so we're adding 1 to the counter, okay, and then we go back um, to here, to the beginning. Okay, so if we execute it, just to see better what I'm trying to say. That's not right, or it's right, because the DFF180 was not changing. It should have changed. Okay, that's stupid of me. Okay, so when I press the right mouse button, you see all the colors happening. Okay, that's when I'm pressing. When I'm not pressing the right mouse button, okay, you see no lines. Okay, and if I press left mouse button, you exit. So that's the right explanation of the code. um, so pressing the right mouse button, you see things on the screen happening, and you're also incrementing a counter. Okay, so let me assemble it, and let's do the initio. Okay, so our program, okay, this one is testing for right mouse button, this one is testing for left mouse button. Okay, if we are pressing the right mouse button, we're jumping here, so we're putting the value in the what the value of is in our counter. So our counter is where is it? 402 44 8p4. So it is here. So all these numbers, okay, because I did 5. Okay, I need to explain something that I didn't actually. Um, so this one is not dc.byte, but dcb. Okay, so it's define constant block. Okay, so we are defining a block. In this case, it's 200 blocks with the binary 101, which is 5. So if we go back to the initio, if we go back, you will see that all our memory, where our counter, where our label is, where our label contatore is, okay, which is here, it starts at 4024489 is 05. So all memory has got 05 stored in it, okay, which in binary is 101, of course. So what he does is we read the value that we have in it's actually here. No, sorry, it's here. Okay, so you will see that this changes. So he reads the byte that is in 8b4. So this one is 8b4, and this is 05. Okay, is this 05? He reads that one and he puts it in DFF180. Then he adds 1 to it and he goes back, okay, to 88C, which is the start, okay, of our code, okay, and tests again. That's what basically he is doing. Um, if we actually, so let's assemble and execute it, okay, and we do left mouse button, right mouse button, and then we exit with the left mouse button. If we go back to the initio, okay, we should see, yeah, so it's 8b4 now, so 8b4, we should see that we do not have 05 anymore, but the value, the counter incremented to the C. Now, what you need to understand that when it reaches 255, okay, it starts again from 0. So this memory address is looping, okay? It's constantly looping, and this is why the pattern is not as big as the um, previous one in previous example, in example one, because uh, wait a second, um, because we have a byte, not like before we were using a word, because DFF006 returns, actually we were reading it and it returns us a word, while here we have a byte. But if we go W and we execute it and we do J and we do the same thing, right mouse button, so we have a counter something and then we exit it and then we do D initio, you should see that now we have a word, and so the address is still the same, 8B4, 8B4, okay, and you can see that our word contains 1005. Oh, that's strange that it happened to be 05. But we define, so yes, you see, it's all of them is 05 now, but they are word. So it happened to be 05. That's really coincidence. Let's do it again. Hopefully, it's not F5. Oh God, it's another 5. Anyway, it's for some reason it's, hold on, are we incrementing a byte actually? So it will always be a 5. Ah, you see how tricky it is. So even if we specified word contatore, okay, contatore is only working. We only specify the address of contatore, which is this address where this one is, but we specified a byte, so it will always be incremented as from 0 to 255. So if we change this to where now, then it will be a different story. And you can see now we have a word, you can see that the pattern on the screen also changed. Okay, so left mouse button, we exit the wait initio. Okay, so now you can see 8B6, and we can see that it's 9, it's a D, 9D3A. Okay, so um, yeah, um, yeah, Crane, thanks. I noticed my mistake. Um, so yeah, you can easily get caught in these type of issues in the 68,000. I made the data.word, but I need to make the instruction also .word. So that's why these things happen. Okay, so let's continue to see what he says about this example to make sure that I have covered everything. The return is returning us to the RTS, okay, here is returning us to the OS, okay. When I say to the OS, we are returning back to Workbench, and on Workbench we have Amos Pro running. So that's what I mean. We're returning back to the program that we launched it from, which is Amos Pro. If we launched it directly from a disk when it booted, that's a different story. There is no OS, and it returns to nowhere. Okay. Okay, so I think I explained most of the uh, things. I'm just checking them. Yeah, the directive end means that whatever follows it is not assembled. Okay, so that's why he could write so much text after it. Um, it's not assembled basically. Um, so yeah, let's see what he says more. Okay, he's saying that the register DFF016 is called POTIMP, a pot input. I think that's what it means for joystick input or mouse input. Um, uh, he emphasizes again about the use of labels. So he gave this memory address where we have the define constant byte. He gave it a label of contatore, and he's using that. Okay, so he's using the label several times just to show an example of how to move from memory to another register, or how to add to memory. Okay. Um, he explains that as in one, which is in our case is as in pro, is intelligent enough that when you use a label and we insert code between as in one, is capable of recalculating the address of where each instruction is, and hence all labels are updated accordingly. So every time we execute it, doesn't mean that the program will go to the same memory location, but the label will be calculated again. I mean, most of the time, from what you have seen, it goes to the same memory location, but it doesn't mean so, depending also what you are coding. I mean, our examples has nothing in memory, so I do not really expect them um, to go elsewhere or to do elsewhere. Also, if you have memory leaks, which it can happen, then that's where you will not use the same memory for sure, because you would have used the memory and it will still be allocated for the OS. This is something that just came in my mind now. I didn't even write it in my notes, but yeah. When you run the program and you immediately press the left mouse button, okay, the address at counter should still have the value of 0. So as I said, it can have the value of 0. That's what I should have wrote there. So basically, it when it exceeds 255, it jumps back to 0. Same if we use word. Okay, when it reaches 65535, it goes to 0. Okay. Uh, to display a memory location, you use the M. Okay, so M contatore, and you can see that what we have where contatore is, it's that memory location. It has got 9D, and you can continue. It's a word, so it's 993A as we saw before, but you can continue to see the memory behind it. Okay, escape exits. I want to finish this example. Did I finish the example? We are here. I just showed the M. Okay, he's saying assemble it again, and this time, but I showed you this. And do not press the right mouse button and check the memory. It should be 0. I already showed you that that is 0 when I did the end, um, when I started in the beginning. As I said, the counter is already a byte long, so from 0 to FF. Um, so we are using labels to indicate positions within the code. However, once assembled, these become memory address. Okay, so just always keep that in mind. To see this assembled with the A and then do a D, what I showed you before, and you can see all where we're jumping to, etc. with the counter. He actually says to modify the code with a word. Okay, so that is something, and he actually did at q.w, but the at q.w is actually add.w, because you cannot have quick, I think, on a word because it's only from 1 to 8. Anyway, it doesn't it you can still write it like that, so it's not a mistake. It's just that it can be confusing. It's a matter of habit of how to write it. You can write at quick.w or you can write to at quick, uh, whichever you like. He explains that um, how to, if the counter was, um, because actually I did modify that code, and here he's using just define constant. uh, Before it was byte, now it's word. So he's not using define constant byte, so where you can specify a range and also where you can specify how many bytes and then the value of the you put in the memory. Okay, so that's something that I already explained. Okay, so here Fabio explains two's complement. I mean, two's complement is, actually I put a note that we can skip it, and I'm not going to explain it actually. I'm just going to say that it's a way of representing a range of numbers, between which is a minus and a plus. If you have 255, you can split 255 in minus 1 to 8 and plus 1 to 7. If you have a word which is 65535, you can split that in minus 32768 and plus 32767. 67. Okay, so that's basically it. I don't think the example he gives here is not really, I didn't like it, so that's why I want to skip it. I think I can confuse you with it, and it is too advanced right now to be thinking about two's complement, but eventually we will cover it. Okay, so when you're using the assembler, okay, this is something that actually I need to enable something on my, yeah. So when you're using the assembler, okay, um, you want to copy and paste, okay, like what we do in Windows. So control, um, control shift, I think control shift B, is it B? Yeah, no, let me read it. Not really having the book next to me. I thought I remembered it by heart. And this is something that I use quite a bit, but it never stick to my head for some reason. I always need to refer to it a bit. Um, so yeah. So if on real hardware, it is, yeah, I did right. On real hardware, okay, it's Amiga plus B, okay, but on WinUAE, it's Amiga Shift B. No, what I'm doing wrong? How can it be? It should be right. Ah, I was not pressing. So it's right control plus B. There you go. Because you have two controls and I was pressing the wrong one. So it is right control, okay? And you can select a block. Then to copy the block is right control and C. Okay, it's copy, it's control C basically. And then it's control and then it is control not P, control V, okay, on the emulator. So control B, I'm selecting it again, and control X is to delete it. Okay, so it's quite similar um, to Windows, but it is I mean, on WinUAE is control, on the real Amiga is the Amiga key, the right Amiga key. Okay. To insert text, you can press Control I. So Control I, you can see that I inserted the text again. Okay. Anyway, which is right Amiga I also. Also from the menu, you have these. So if you are here, you can block. You see they are here: Amiga B, Amiga C, Amiga X. Okay, so it is control, control, control. So the right Amiga is replaced with control, right control. Sorry, it's important that right control. If you press the left, and I'm left-handed, so I was pressing the left one. It's an issue. It will not work, as you saw. I'm going to finish this example, okay? But we are nearly done. Um, the above key explanation tells us to copy the second source. So basically, he's telling us to modify the code and what I just did with Word instead of while I did it um, on the code specifically. Okay. And then to do the debug as we did. So I'm still reading from the book. Okay, so then to copy and paste what we did, basically it just and using the M command and the D command to show the memory, which I do not need to. And he explains the Amiga X, which you can see here, which I explained, and then he explains binary, which you can see them here. Um, these are the hex numbers, so from 0 to F, what they mean in binary and what their value is, and he explained it in a nibble basically. Well, he continues, but till F it's a nibble, no? So the first four. It is recommended to use .s or .w when with these instructions. So these four instructions, actually these two, because branch and branch to subroutine do not um, no, I correct myself. um, branch and branch on and branch on equal is after a condition, okay, while these two don't take a condition. They also take .s or .w, so you can branch. It's like a jump, but on 6502, but this is plus 1 to 7 or minus 1 to 7, or sorry, or plus 1 to 7 and minus 1 to 8, or if it's word, whatever the number is, because right now I cannot remember. But yeah, you know what I mean. It's to complement what I mentioned before, those two numbers. And same for branch on equal, branch on not equal. Okay. There are when I have the text many times, I do not see your messages, guys. So if you send a message, I will have to reply later on. Um, he also, so this is how this is why I had defined constant byte, because I was experimenting with the source myself. Um, he explains that define constant bytes means you define 200 bytes and you fill them with 0. Okay, that's what he's saying here, and we did that. I showed you that in the example. So basically, we finished the first example, okay, in uh, in chapter 2, and we just covered addressing mode, one addressing mode, which is absolute addressing. Um, as I said earlier, I will be trying to raid the channel, so please bear with me for a second. However, I would like to thank everyone again. I do have a list, Crane, if you, because he sent me a message, have a list of all the people that you need to thank. But I do have a list, and I need to say uh, thank you to all the people that helped me or help in some way to the channel. They are all in my thanks, but there are some people that I need to thank specifically, like the retro programmers inside the group. They do help me quite a bit. I need to thank, of course, Fabio Ciucci for allowing me to do this. Um, Also, I need to thank Shalan and Old School Coder um, for, you know, none of them are here today, but I do follow Shalan and Old School Coder, and basically I'm in their Patreon program too. But what I mean is I learn a lot from them, so I have to thank them also when it comes to 6502 programming. Um, of course, I think all the Phase 101 members, the Commodore Dev group, and the Phase 101 group. So let me try to see if I can raid a group, because, or a channel, if there is anyone online, because right now, oh, there is Mike. I'm going to raid Mike, to be honest. And yeah, and I'm raiding him now. Thank you very much.